Welcome to Breadboarding. In the previous video, we looked at the AND, OR, and exclusive OR logic gates, and we also looked at a buffer here, which is used to boost the signals to go along bus rails. So we had this strip board bus rails that I've used in the earlier series. And we also connected one of the oscilloscope probes down the end of this, and you can see here the wire from the output of this crystal oscillator is going all the way up to the top of the board here and then down these rails. And you can see on the oscilloscope trace here that we've got about a 3.6 megahertz signal here, but because of the electrical characteristics of the bus rail, so things like impedance and capacitance, we've got quite a lot of ringing here on the transition of the signals. And in particular, you can see here that from down the bottom here, we've got almost about minus 1.7 volt sort of spike as the signal switches. And you can see this ringing, and also less so when it actually gets to the top here. So we're not going to look at solving that during this video. That will be coming in a couple of videos time. But there was just one other issue that I'd forgotten to cover during the previous video to do with these buffers. So this is the fan in, fan out for the 74 ALS 541 buffer. Now, if we actually have a look at the table that we looked at in an earlier video, you can see that the standard LS and ALS are able to drive about 0.4 of a milliamp for high outputs and up to about 8 milliamps for low outputs. And that gives us a fan out of about 20. So that means that one output can drive about 20 of the equivalent inputs. Now, if we have a look at the data sheet for the 74 ALS 541 and we scroll down and look at the appropriate section, so you can see here this is the ALS 541, you'll see that the output current for high can be up to 15 milliamps and for low can be 24 milliamps. And then down here we'll also note that in fact the input current is in fact 0.1 milliamps and the high level is 20 microamps. So this is actually a bit lower than the standard. And if we go back to our slide, you can see that with the 15 milliamps and 24 milliamps and the 20 microamps and 0.1 milliamps, that 0.1 milliamps is actually half of what the normal ALS is, and it's about a quarter of what the original LS is. Now what that means is that if we were connecting ALS buffer to ALS buffer, then the fan out for the high signal is about 750 and for low is about 240. But then if we then look at the 0.2 and 0.36, that still gives us a worst case fan out for ALS to ALS of 120. And if we were connecting ALS to LS, then that would still be 66. So you can see compared to the worst case fan out of the original TTL of 10, then 66 or 120 is much, much better. So if we're using these 541 type buffers, then that will hopefully eliminate any sorts of problems with running out of fan out capacity. So this is video 9 of the how to use breadboards and retro digital electronics, and in this video we're going to be looking at the NAND, NOR and exclusive NOR gates. So these are like the inverse of the gates that we were looking at in the previous video. So in the previous video we covered the AND, the OR, the exclusive OR and also the buffer. We did the inverter or the NOT gate in 2 videos ago. And in this video, we're going to be looking at the NAND gate, so the negative AND, the NOR, the negative OR, and the exclusive NOR gate. So the NAND gate is probably the gate that is used the most in digital electronics. And the symbol is basically just the AND gate with the circle on the end, just means that the output is inverted. And if we look at the truth table here, if you remember, the AND gate required a 1 and a 1 to get a 1, and all other values were 0. But because this is inverted, then the only time we get a 0 is with a and B being 1. And the rest of the time we get 1s for any other combination. This is the KiCad schematic, and you'll also might see that it will be done as an AB, it's kind of A multiplied by B. Sometimes you'll also see a dot in there as well. And the bar over the top means that it's inverted. So it means A and B inverted. Now, as far as the different types of gates, then there's a selection here. There are a few more than this, but these are the main ones. So the most common one you'll come across is the 74LS00, and this is the 4 2-input NAND gate. So you can see we've got A and B inputs, Y output, and we've got 1, 2, 3 and 4. Now, if you'll notice the direction of these gates, this is the standard direction that most of the chips have. When we come to the NOR gate, you'll see that this is actually reversed. And then we've also got combinations with 3 inputs, with 4 inputs, and also even with 8 inputs here. And basically, all these things are pretty much the same in that you will only get a 0 coming out of these when all of the inputs are 1. So let's take a look at our breadboard and just do a quick test of a 74LS00 NAND gate. So this is our circuit. If we just zoom into, so we've got our blue LEDs, just power, just to make sure that we know we've got power on. We've got our little mini voltmeter down the bottom. We've got our A and B input LEDs, and then we've got our output Y LED. So the Y LED is green, the 2 inputs are red. So when we have a 0, then they'll be off. And when we have a 1, then they'll be on. So you can see that we've got 2 wires for A and B. So A is blue, B is red. So at the moment, they're just loose free. Now, if you remember in the previous video, that TTL inputs tend to have an internal pull-up resistor. So if we don't have anything connected to it, then it will tend to default to high. Now in the AND gate, that meant 2 highs would result in the output coming on. But in fact, with this case, when we get 2 highs, then in fact we get a 0. So when we switch this on, we wouldn't expect the green LED to come on because a 1 and a 1 gives a 0. So we've just got the LEDs are just tied to the input pins through 1K resistors, and then the output here, because the output isn't quite as high as 5 volts, got a slightly lower value resistor, 330 ohms there, that drives the green LED. So let's turn it on. So you can see the output LED does not come on by default. So if we go, if we put both zeros first, so both the 0, we don't have any lights for A and B, but we do have the output. If we do A is 1, then we have A is on and the output is on. We do B is on, and again we get B on and the output on. But when they're both on, then the output is off. So that's very simple NAND gate. But one of the key things we're going to come to have a look at, that the NAND gate can actually be used to build all other gates as well. So we'll look at that in a few minutes. So that's the NAND gate. Now the NOR gate is just the OR gate, again with an inverter on the output. And if you remember, the OR condition meant that we would get a 1 if either of the A and B were 1 or if both were 1. Whereas with the NOR gate, the only time we get a 1 is when A and B are 0, and then all the other combinations, we all get 0 there. You can see the KiCad schematic here, and the logic rules quite often show an OR as A plus B, and the bar just shows that it's inverted. And again, you'll see on these things, it's the same syntax there as well. Now, if you'll notice, the 74LS02 is a little unusual in that the direction of the gates is actually reversed from the normal direction. So if you don't put chip labels on these things, it's very easy to assume that all of the inputs are 1 and 2 and the outputs 3, and this would catch you out. I'll just show you the previous one. You see, this is the 0, 0 in the NAND gate, and this is the NOR gate. So it is a different way around. And the NOR gate has a similar variety, not quite as many as the NAND gate. They've got a 3-input NAND gate. We've got open collector version, so this means that the output here is probably capable of sinking a larger current, but doesn't have any pull-up or totem pole pull-up. So we'd have to include a pull-up resistor on the outputs of those if we wanted to see a high level. And then there's also a 5-input NOR gate there as well. Let's look at our circuit and switch it over. So I'm just going to pull the chip out. Now, because the chip is actually slightly different, what I'm going to do, in fact, is just shift this up a couple of slots, because then it means I don't have to rewire all the LEDs. So I'm just trying to make this such that here we go, so the output is there. That just means that I don't have to rewire the 2 input LEDs. I just need to move this And then we just need to attach the output to pin 1. Okay, so we now should have those two inputs. So when we turn this on again, because the inputs will default to high, so by default without anything connected, then we would expect to see a 0 coming out of here. And then the only time we're going to get a 1 is when they're both connected to ground. Let's just disconnect those to start with. Turn on the power. The power is on. So again, we don't see the output Y. If I connect both of them to ground, then in fact we get the output is 1. When A is 1, we don't get the output. When B is 1, we don't get any output. And when both A and B are 1, we don't get any output. So again, that's what we'd expect with a NOR gate. Now again, the NOR gate is a useful gate in that we can also make any other gate with a NOR gate. So both the NAND and the NOR gate allow us actually to create any other gate from them. Won't necessarily be the most efficient way of doing it, but it certainly allows us, if we had spare gates on a NAND or a NOR gate, we wouldn't necessarily have to add another chip. We could make up some of the other gates with the unused NAND and NOR gates. Then we come to the exclusive NOR gate. Now I'd have to say the exclusive NOR is not very common. In fact, I think there was only about one chip I came across, the 74LS266, which is a range which isn't commonly stocked. You may probably have to go to a major distributor like Mauser or something like that to actually get these, and I don't actually have one of these in stock. And the exclusive NOR is very similar to the exclusive OR. So the exclusive OR would only give a 1 when the A and B were different. So if they're 0 and 1 or 1 and 0, and because this has got the inverter on the output, then in fact the only time we get a 1 is when A and B are the same. So if A and B are 0 or A and B are 1, then we get a 1 output. And again, the schematic for this is from KiCad, and the exclusive OR symbol is this kind of plus with a circle around it, and then the bar over it then inverts that. And you'll see that in fact in the TI databook here, then in fact the symbol they use for XOR is different. So this is one of the confusing things you can come across, in that the symbols used for some of these things will vary depending on the sources which you're working to. So it can take a little while to work out that they're actually the same thing. Now, because I don't actually have one of these chips, what I thought I'd do is use this as an opportunity to introduce you to programmable logic devices. Now, there is a whole playlist and a whole series on programmable logic devices, so I'm not going to reproduce all of that, but I will just take you through a little bit of what a programmable logic device is, and I'll show you how we can actually make an exclusive NOR gate, and we can actually test that. So there will be a playlist at the top of the screen here for the Programmable Logic Devices series, and I'll also include it in the description below the video. And the chip we're going to be looking at is the ATF22V10. Now, there's a history of all of the Programmable Logic Devices and their names like PALs, GALs, and things like that. They're all pretty much synonymous with modern Programmable Logic Devices. The current ones, you can still buy these. I think the 22V10 is about £2, probably about $2.50. There's a slightly smaller version, the 16V8. It's a bit cheaper. It's only about £1, about $1.20, $1.30. However, they're a little bit more complicated to get working correctly. These are probably simpler to use. So I'd recommend, if you're doing things with PLDs, use a 22V10 by default. It's a bit easier to use than the slightly smaller, cheaper ones, but the smaller, cheaper ones can be used in certain circumstances, and I cover that in the series. Now, you will need a compatible EPROM programmer, so generally these sort of EPROM programmers can be used to program these PLDs. I'm actually using an XGECU T56. Now, this is a fairly expensive one. It's now been replaced by the T76, and it does cost quite a lot. You can get a cheaper version. The one I used to use was, I think, an 8662. Unfortunately, I've misplaced it. It's buried under a pile of equipment somewhere. I couldn't find it. That has been replaced by the T48, which is only about £52. Just be aware, however, that some of the chips I use in the PLD series can only be programmed by the higher-end programmer, The one I'm showing you here will work with this T48, but just be aware and watch the whole series before you go out and buy a programmer. Make sure that you're happy to the trade-off that the cheaper programmers will do a lot of things, and to be honest, it's only the more exotic chips that you will need the high-end programmer for. So there is a video link here, and again I'll include the link in the description below. So I'll just show you that video. So during this video, it's probably about up to an hour introducing what programmable logic devices are, but as part of that there is this example. Now the gates.pld comes with the utility which is used to compile these files into the sort of .ged files that you need to program the chips. And WinCUPL was a bit dated and hadn't been updated really since Windows XP. But there is a new version out. It's still in beta, but it's pretty stable, and it's been out now for about 6 months, so I'm not quite sure when that will go to full version 1 release. But I covered in this video the background to PLDs, how to program them, how they work, and all this sort of stuff. So I'm not going to reproduce that here, but we are going to look at using this file. So this is a PLD file. It's just a text file. There is a certain amount of stuff that you have to have in it, and you need to delimit lines with a semicolon for WinCUPL to actually interpret it. Comments are pretty much standard sort of comment syntax. I always tend to put a chip layout on here. I just find it helps to visualize what's going on and to help lay out things in the optimal way. We need to say which label we're associating with each of the pin inputs. You can also see we have an output enable here as well, and the output enable has an exclamation mark by it, and what that basically means is that that will be active low. So when we put 0 volts on there, then in fact the OE term within our PLD here will actually be true, even though the value is negative, as it were. So this active low input having an exclamation mark on the definition means we only ever have to worry about them being true in the rest of the logic rules. And you can see here we've got inverted A, inverted B, AND of A and B, NAND of A and B, OR of A and B, NOR of A and B, exclusive OR of A and B, and what we want here is the exclusive NOR of A and B. So pin 21 is going to be the thing we're going to be using. And then you can see down here that the logic rules are fairly straightforward. So the inverse of A is just exclamation mark A. The AND of A and B is just A and B. The NAND has just got the exclamation mark in front of it. OR actually uses the hash sign or the pound sign for Americans in the OR there, and NOR just has the exclamation mark. And in WinCUPL, the CUPL language, then the dollar is actually an exclusive OR, and then to do an exclusive NOR, we just have the invert of that. And then you can see then that the output enables on all these outputs is actually set to OE. So it does allow you to actually configure the output enable can actually be configured by gate, should you want to. So that's our PLD file. Now, in order to actually program the PLD, what we need to do is first of all compile it in WinCUPL, and then we need to use our EPROM programmer to actually then write the GED file into the device itself. So if we just copy the file path, so if you go to this URL here, so this is the URL for the new version of WinCUPL. Whatever you do, don't use the old version, it's pretty flaky. And this is the documentation for the new WinCUPL. You can see you can download the beta there and install it. I may do an update video to the PLD series to cover this, but what you need to know is here. So when you install and run up WinCUPL, the only downside to the new WinCUPL is that in order to compile a chip, what you need to do first of all is create a project file. So there's an extra step here really that you didn't necessarily have to do previously. So you need to choose what the device is. So we've got an ATF22V10C. It is important to make sure that you match the exact model here, because there's variations of differences in the different models there with different capabilities. We've got the 24-pin DIP, so that's a dual inline package. That's our breadboard compatible. You can see there are various other sort of flat pack forms. And then there are some options here. So this is the power down mode, and I think there's a user extension area where we can put a few bits of information, but we don't need to use that. So we're going to create the project. It's warning us that the path can't be longer than 127 characters. Then we need to produce a file name for it. What I normally do is just put our Gates PLD file, and what it will say is that there's already a PLD file there, so I'll add it anyway. And so you can see we've got our Gates PLD, and there's just a few things we need to go in to do. So we want to go in for the output files and say we want the document file to be produced. Sometimes you might find you need to enable some of these optimization and minimization features. For this simple one, we generally don't need to do that. Then once we've done that, if we just save it, we do a compile. It'll take a few seconds to do this. It's completed. If there are any errors, we would get the errors down here. You'd need to go through and sort that out. So the most useful file produced, other than the GED file, is the file that we need to use for the programmer. But the .doc file, which is not produced by default, you have to go into those options to enable it. And what you'll see that the doc file does is actually gives you a chip diagram. So this is actually produced by WinCUPL itself. So if you've made a mistake in the mapping of the pins and you've got the pin numbering wrong, then you'll probably find that these things won't quite look the same as the pin layout that you've got at the top. This section here is the fuse map, and in the PLD series I explain exactly how you can work out what that means. I mean, you don't need to know about it in order to use them, but it's helpful, I think, sometimes in trying to diagnose certain problems. Then we've got the logic rules up here. So this is showing us that our exclusive OR is actually broken down into A and not B, or not A and B. And what we'll see when we come to one of the slides later, that in fact this is exactly how exclusive OR and exclusive NOR can be implemented using individual logic gates. And the symbol table here, this is also quite useful in that if you see one of these labels here and there's no pin number associated with it, it is likely that you've got a typo. So these names are case sensitive, and so if you accidentally put a capital N in there or something like that, you might find that there's a zero or that there's a gap there, and that would actually indicate it's created another term here, and you probably are going to end up with problems with your PLD. So look for any gaps here. There are circumstances where gaps here are okay, particularly if you're using fields and things like that. But in general, when we've got a simple one like this, if you've got a label here without a pin assigned to it, it probably means you've got a typo somewhere. So we've got our GED file. So the GED file is a JDEC sort of programming file. And so what we need to do now is to run up the EPROM programmer utility. So this one uses XGPro. So you can see here we've already got the chip is already selected. Previous chips you've used, you can see are here. So the ATF22V10C, for example, is a slightly more sophisticated version of this. And to program that chip, you do actually need the higher end programmer, for example. But we're okay with this. You can actually search for the devices. We don't need to worry about that. So we've got this particular device. I'd always recommend whenever you're using one of these is read the chip first, because if you put it in incorrectly, it will tell you that it can't read the chip. And if you try and write to the chip first, then you may damage it if the pins aren't inserted correctly. And generally when there is a blank, then it should all be ones. So these chips, when they're erased, tend to have all ones there. Now we need to load the GED file. So you can see there's just the gates.ged file. And you can see when we load that, then an awful lot of the terms have actually been zeroed. You'll see there's a few here with ones, but the vast majority of these will have zeros in. And again, I explain what all those things mean in the PLD series. So now all we need to do is to program it. We're going to undo the lock bit because that basically means we can't read the configuration back. And that, for when we're doing this sort of development stuff, then we want to be able to do that. So we'll just program that. Okay, so that's done. Now we could just now use our chip, but there is a useful feature in the programmer software here, and this allows us to test chips. And what you'll see here is a standard library of virtually all the common CMOS 4000 series and all the 74 LS series as well. So for example, if we wanted to test one of our NAND gates, for example, we could use that one, and you can see here there is a set of test conditions for that. But I happen to know that I've got one already in here for the gates So this is a test condition for the gates, and what we can just do is to run the test, and it says it's all normal. Well, that's a bit boring, so let's have a look and see what it does. So you can see we've got the pin layout of the chip, we've got the 5 volt and ground, the 0 and 1 show inputs and what value are. An output of X means we don't care, but you'll see that these various conditions have highs and lows. So if you look at number 5 there, and we've got pin 14 here is low. So if we change low to high, modify the line, save that and test it, we'd expect that to now fail. And you can see here we've got a red there that says this is failed. So using this to test your PLDs is quite handy. Just change this back again. Test it again. This is quite handy. The only downside is that we can't put labels on the top here. So what I tend to do is define the rules in something like a spreadsheet. So you can see here we've got A and B as the inputs here, and we've got all the various definitions here. And this basically shows us for our exclusive NOR for the different combinations of ones and zeros here, whether we expect to be high, low, low, high. And then when the output enable is set to 1, then in fact we'd expect it to be high impedance, so there wouldn't be any output driven at all. So you can see there that it has also managed to test that our output enable is working properly as well. So I just find it easier to do the rules like this, because then you can have a little description for what number 5 means, rather than just having to guess what it means in the tool itself. This is our programmer and the chip, and I've also put a chip label on there as well. So this is the chip label for that particular one. So we've got the inputs A and B, and then we've got all the various gate outputs there as well. So I've stuck that on there. So just turn it off and wire it up. Again, A and B are actually offset slightly, so this VCC is in the right place. We just need to move where our ground is. So you'll see that these chips are a fair bit longer. They're 24 pins. And one of the reasons why you might use one of the 16V10s is actually a bit shorter. So now the output, rather than being pin 1, we want the exclusive NOR, which is in fact this pin here. And again, the A and B are connected to these two here. Now what we do need to remember is we have the output enable there. Now by default we know the output enable is likely to default to high, so if we don't actually put a link in there, then we may not actually see anything. So we need to put the output enable to ground there. So we can see that our output is in the exclusive NOR, A and B are on pins 2 and 3, and so we'll now try that. So we've currently got the inputs to 1 and 1, and that we would expect to give us 1. We have 0 and 0. We've also got 1, and then we'd expect that when we have 0 and 1 and 1 and 0, then we would have 0 out. That's 0, 0. Now, if you want to do XOR as well, then in fact we could go to the XOR here. So in this case, when they're both the same, we get 0. When they're different, we get a 1. Same, different. So you can see we could have actually done all of the logic gate tests that we've done over the series so far, actually using this one chip. Now, one of the things you may come across, certainly in older documentation, and this is an example, the IBM PCXT schematics from 1983, I think this was. If we just zoom in here, I'll explain what I mean. Do you see where we've got these gates with the purple dots around them? These are looking like, this looks like an OR gate, but it's also got these circles on the input, so there's negative inputs here. Now in actual fact, this LS10, this is in actual fact a 3-input NAND gate, but it obviously doesn't have the AND shape here. And similarly here we have an OR type symbol, but because we've got the inverted on here and inverted on there, then in fact this is actually a 2-input AND gate. So the 08 was an AND gate in the earlier videos. And similarly down here we've got a 3-input one and a 2-input one. This one in particular is the NAND gate, so the LS00. So you can see here that, again, this is the OR without any invert on there, but with inverted inputs there. And then over here as well, we can also see that these are the AND type symbols, but they've got the invert negative on the output and on the inputs. And in fact, this is an LS32, so this is an OR gate. So this is really quite confusing. And there are two ways of actually representing gates, and this is using negative logic. And when I first sort of came across this, it took me a little while to get to the bottom of why this was being done. But there is quite a nice diagram from Hyperphysics URL here, which again will be in the description below. And what it basically shows us, if we use this negative logic, then we can represent an AND gate as this sort of, what I would say, a NOR gate with two inverters on the inputs. So in fact, that what this is showing is that A and B is the equivalent of the invert of A and the invert of B ORed together and then invert the output. There's a whole topic on logic to do with De Morgan's theorem and all sorts of stuff, which lots of other sites, in particular the computer science ones, will probably handle a lot better than I ever could. But in practice, what this really means is I'll go through what the symbols are and the schematics, what each one of these means. So it basically means if we want to get an AND gate, so an AND gate is the equivalent of an NOR gate with two inverters on the inputs. Then we look at an OR gate. That OR gate is the equivalent of a NAND gate, negative AND, with two inverters on the A and B inputs. When we look at a NAND gate, that is the equivalent of an inverters going into an OR gate. And when we have a NOR gate, that is the equivalent of an AND gate with two inverters going in it. And then finally down the bottom for inverters, I've mentioned previously, if we have either a NOR gate or a NAND gate and we tie both the inputs together, that effectively makes an inverter. So what you can see here is, if we wanted to, what we could do is with three NOR or NAND gates, we could actually make up one of these. And you can also see even these ones that don't have the inverted one, we would have to use another gate to do the inverter on there. So, but it's not very efficient to use a NAND or a NOR gate to build all these other gates, but it certainly is possible. And certainly if you're simplifying rules and things like that, if you have more complex combinations of things, you may very well find that there is a simpler combination that actually achieves the same inputs and outputs. And one of the things that WinCUPL will do is, with some of the optimization modes on it, it will simplify the rules that you defined and actually give you the minimum set that you require to actually implement your logic. So that's all I was going to do for this video. And you can see now we've done sort of 9 videos. So we've done the basic gates and logic and all of the voltage levels and things like that. What we're going to start to do now is to look at perhaps more useful implementations of this. So looking at decoders and multiplexers in the next video. And in particular, what I'll be doing is looking back at some of the projects I've done over the last couple of years. And we'll actually look at where these different decoders and multiplexers are being used. And as we go through this, when we get to the end here, what I'm actually going to be doing is looking at all of these TTL logic gates which were used in the original IBM PC XT and in the CGA video card. And I'll actually go through and see if there's any that we haven't covered. So basically, once you've got to the end here, you should actually know how all of the basic logic gates work needed to make a working PC. And during all the other series of videos, I have actually covered all of the other more exotic chips, so things like DMA controllers, serial controllers, PS2 keyboard controllers. So with all of these series, you'll actually know exactly how a PC really works. So in this video, we've looked at the NAND gate, the NOR gate, the exclusive NOR gate, and we've also looked at how we can use programmable logic devices to actually make combinations of logic gates into a single package. So we don't need to have, say, 4 different chips to actually be able to have all these combinations that we've got on this chip. So if you don't want to miss out on future videos, please hit subscribe. And if you could hit like as well, if you found the content interesting and useful, it just helps to make the videos available to more people. Thanks for watching.